When we talk about the sun, we often think of it as that burning golden disk that rises every morning, warm, familiar, predictable. But what if I told you that the deeper we look into it, the stranger it becomes? What scientists have uncovered in recent months is nothing short of astonishing. For decades, we believed we understood the sun's basic anatomy, its surface, atmosphere, and core. Yet the newest images and data reveal something far beyond expectations. The deeper we see, the less familiar it feels, as though the sun itself is rewriting everything we thought we knew about the star that gives us life. NASA and ESA's combined solar observation programs have now pierced deeper into the sun's layers than ever before, exposing movements, patterns, and forces that seem almost alien. Forces that defy current solar models and challenge our very concept of what a stable star even is. What's happening inside this massive sphere of plasma is not calm. It's chaotic, alive, and unnervingly complex. It started with the joint effort between NASA's Parker Solar Probe and the European Space Agency's Solar Orbiter, two spacecraft designed to get dangerously close to the sun's scorching outer atmosphere. Over multiple flybys, these probes sent back signals and images from regions never before observed. What they found shook even the most confident astrophysicists. In the plasma zones near the transition layer, that mysterious boundary between the chromosphere and the corona, something entirely unexpected emerged. Instead of the smooth transition scientists predicted, there were vast, shifting voids, pockets where energy seemed to vanish. These strange cavities behaved almost like invisible whirlpools, twisting magnetic fields and swallowing radiation in unpredictable bursts. They weren't supposed to exist, and yet there they were, repeating across multiple wavelengths. Some researchers began calling them ghost zones, regions that seemed to disrupt the sun's magnetic rhythm. As the data streamed in, the instruments recorded a pulsing fluctuation coming from deeper than the chromosphere. A strange rhythmic beat, like the sun's own hidden heartbeat. For years, astronomers had measured acoustic oscillations on the solar surface, tiny ripples caused by internal pressure waves. But these new readings were something else entirely. They were deeper, slower, and more erratic, hinting at vast internal motions beyond our models. Every 43 minutes, a pulse rippled outward, faint yet unmistakable, suggesting that inside the sun there may be dynamic structures, shifting and twisting far below the visible surface. These movements appeared to correspond with spikes in solar activity, linking deep interior processes to solar flares and coronal mass ejections at the surface. The implications were staggering. The sun's core might not be as static or uniform as we once believed. Instead, it could be a living ocean of plasma currents, where energy surges rise and collapse in waves spanning thousands of kilometers. But what came next was even stranger. As researchers pushed further into the data, they found regions of reversed flow, zones where plasma appeared to move inward rather than outward. It was as if gravity itself momentarily bent backward within localized areas of the sun's convective zone. How could plasma, heated to millions of degrees, ever flow back toward the core instead of exploding outward? The initial thought was that it had to be an error, perhaps interference from radiation noise or instrumental anomalies. Yet after repeated analysis and confirmation by both Parker and Solar Orbiter, the phenomenon proved consistent. These reversed flow channels formed briefly, lasted several minutes, and then vanished. It was like watching the sun inhale and exhale energy, almost breathing. To visualize these processes, scientists created composite images using extreme ultraviolet and X-ray wavelengths. The result was astonishing. Beneath the turbulent surface, they found thread-like veins of magnetic energy, interlaced like neural connections in a brain. Each filament seemed to spark and pulse independently, releasing bursts of radiation that could heat the corona, the sun's outer atmosphere, to temperatures over 1,000,000 degrees hotter than the surface below. This revelation reignited one of solar physics' longest-standing mysteries. Why is the corona so much hotter than the sun's visible surface? The deeper data only complicated things further. Instead of finding a steady transfer of energy upward, they saw chaotic, localized surges, microflares, and nano-explosions happening thousands of times per second. It wasn't a smooth flow of energy at all. It was a frenzy. In one particularly haunting image, scientists observed a pattern that seemed almost biological. The plasma filaments didn't just flow randomly, they twisted into spirals, interlocking like strands of DNA. Each rotation was driven by immense magnetic tension, and when the twisting became too intense, it snapped, unleashing explosions that hurled matter into space. Some of these eruptions extended hundreds of thousands of kilometers, forming coronal mass ejections powerful enough to disrupt Earth's magnetic field. When viewed in motion, the entire sun resembled a colossal living organism, breathing, flexing, and reacting, rather than an inert ball of burning gas. What was once the simple star at the center of our solar system now appeared more like a vast, conscious machine, governed by invisible electromagnetic laws. For the first time ever, the probe's data allowed scientists to simulate these structures in full three-dimensional models. The resulting renderings revealed that what we see as the sun's surface is merely the skin of a much deeper storm. Beneath it lies layer upon layer of rotating plasma sheets, sliding past each other like tectonic plates on Earth, but at unimaginable speeds. At the boundaries where these sheets collide, magnetic tension builds until it violently releases, sending shockwaves up through the photosphere. These unseen collisions could explain why solar activity rises and falls in an 11-year cycle. It's not simply about magnetic fields reversing, it's about deep interior layers grinding and snapping in cyclical motion, a solar heartbeat on a cosmic scale. Even more unnerving was the discovery of what researchers dubbed dark threads. These are thin, cooler channels of plasma that weave downward through hotter regions like cracks in glass. They seem to act as conduits, siphoning off heat and energy from the outer layers back into the interior. Why they form remains a mystery, but they may be tied to the reversed plasma flows observed earlier. It's as though the sun is constantly rebalancing itself, taking energy from one region and redistributing it elsewhere, maintaining a delicate, dynamic equilibrium. Some have begun comparing it to Earth's weather systems, where hot and cold air masses interact chaotically, generating storms, cyclones, and pressure waves. The sun's weather, however, is infinitely more violent, with storms capable of engulfing entire planets in their path. Yet, despite all this new knowledge, the sun continues to guard its deepest secrets. The Parker Solar Probe is expected to complete its closest approach in the coming months, skimming just 6 million kilometers above the sun's surface, a terrifying distance considering the temperatures and radiation levels there. Every time it dives in, it's bombarded by plasma and light intense enough to vaporize metal in seconds. Only its carbon composite shield keeps it alive long enough to transmit precious data back to Earth. And each time it does, the patterns become stranger, more intricate, more alive. The deeper we see, the less we understand, and that's what makes it beautiful.
As Parker plunged closer to the blazing inferno, something unprecedented occurred. The probe crossed what NASA scientists call the Alphen critical surface, a turbulent boundary where the solar wind transforms from a bound, structured flow into a wild, chaotic blast of particles streaming freely into space. No human-made object had ever entered this zone before. The readings that came through were nearly incomprehensible. Instead of smooth, outward-blowing plasma, Parker encountered pockets of reversed flow, gusts of charged particles shooting back toward the sun. It was like flying through a hurricane that suddenly reversed direction. Instruments designed to measure solar wind density began spiking and dropping wildly, suggesting that the sun's outermost layers were not merely radiating energy outward, but were folding it inward in complex magnetic loops. It wasn't a one-way process as previously thought. It was a storm of feedback, where the sun appeared to feed on its own expelled energy, recycling it in waves of magnetic turbulence. This discovery forced scientists to rethink fundamental solar models that had stood for half a century. Back on Earth, as the data came in, scientists noticed something eerie. Every major fluctuation Parker recorded corresponded to subtle, measurable disturbances in our planet's magnetosphere. The Sun, nearly 150 million kilometers away, was somehow vibrating Earth's magnetic field in real time. It was as if the stars' internal rhythms were whispering across the void, syncing with our planet's heartbeat. What's more, these oscillations appeared slightly ahead of schedule compared to solar flare emissions, almost as though the Sun's deep interior pulsed seconds before the surface responded. Could the Sun be warning us before it releases massive solar storms? The possibility opened new frontiers for space weather prediction, and new fears. If we can decode these pre-flare pulses, we might have precious minutes of warning before a catastrophic blast of charged particles strikes Earth, disrupting power grids, satellites, and communication systems. But not all the findings offered hope. The deeper the analysis went, the more anomalies emerged. One of the strangest was a repeating signature buried deep within the data, a low-frequency vibration that didn't match any known solar oscillation. It pulsed steadily every 88 hours, unlike anything seen in the Sun's rotation or magnetic cycles. At first, it was dismissed as an artifact of instrumentation, perhaps a timing glitch or data compression artifact. But when the same pulse appeared independently in data from the solar orbiter, positioned millions of kilometers away, the coincidence could no longer be ignored. Both spacecraft, operating separately, detected the same rhythmic beat echoing from deep within the Sun. Some scientists now speculate it could be the resonance of large-scale plasma flows colliding inside the convective zone. Others suggest it might represent unknown interactions between magnetic field layers, a kind of solar resonance that oscillates like the ringing of a cosmic bell. Visualizing this, researchers generated a high-resolution map of magnetic wave activity beneath the surface. The results were mesmerizing, vast, luminous rings of plasma, spiraling inward, overlapping like ripples in a pond. At the center of these patterns, certain regions flickered intermittently, dark zones surrounded by brilliant arcs. When the wavelengths were analyzed, the dark regions turned out to be slightly cooler but magnetically denser than anything around them. Some describe them as magnetic knots, where field lines twist so tightly they almost cancel themselves out, creating pockets of suspended motion, areas that appear frozen amid chaos. But here's the bizarre part. Those frozen regions weren't stationary. They moved, slowly, deliberately, almost purposefully, drifting across the inner surface of the Sun like patches of shadow sliding through light. Their origin and behavior remain unexplained. And then came the most unsettling revelation of all. During its fifth close approach, Parker's magnetometers detected a sudden massive distortion in the local magnetic field, a wavefront so large it temporarily overwhelmed the sensors. When reconstructed, it appeared to originate not from the outer layers, but from beneath the visible surface. This subsurface wave rippled upward, releasing a colossal flare just hours later. The timing was too perfect to ignore. The flare was preceded by the deep magnetic pulse, proving that the Sun's internal layers were directly influencing its surface eruptions. What shocked scientists was the shape of the pulse. It wasn't random or diffuse, it had symmetry, like a geometric vibration radiating outward from a point source. Some researchers privately speculate it might hint at organized flow patterns deep within the Sun's core, perhaps even structures we don't have the physics to describe. As simulations improved, the picture grew even stranger. Models based on Parker's readings suggested that deep under the photosphere, enormous vortices might be churning, plasma storms larger than Earth itself, rotating in opposite directions, colliding and merging in cycles that last months. Each collision generates a surge of energy that propagates upward through the layers, culminating in the violent eruptions we see as flares or CMEs. The Sun, in this sense, behaves like a colossal living dynamo, continuously building and releasing tension through rhythmic, almost organic processes. Scientists began referring to this phenomenon informally as solar respiration, the Sun's way of breathing energy into the cosmos. In ultraviolet wavelengths, the solar orbiter's imagery confirmed another bizarre detail. Certain regions of the Sun's corona flicker in coordinated patterns across vast distances. One bright region would dim while another flared, hundreds of thousands of kilometers away, perfectly synchronized. The synchronization happened too quickly to be caused by normal wave propagation. Something was linking these distant zones instantaneously, as if the sun's magnetic field were acting like a vast interconnected nervous system. This raised questions that bordered on the philosophical. Could the sun's magnetic field operate as a kind of self-regulating system, adjusting energy flow in real time? Was the sun more than a chaotic sphere? Was it aware in some mathematical or energetic sense, constantly recalibrating its own balance? For all its awe-inspiring beauty, this discovery carried a quiet sense of dread. If the sun's interior is this volatile and unpredictable, then our understanding of solar cycles and our planet's safety might be far less certain than we assumed. The more we see, the clearer it becomes. Beneath that golden glow lies a storm unlike anything else in nature. A storm that never ends.
As the scientists dug deeper into the high-resolution data, they encountered phenomena that defied not only expectations, but also decades of theoretical modeling. One of the most startling discoveries was the existence of vast plasma tunnels, elongated channels, thousands of kilometers long, where energy and particles moved almost independently of the surrounding material. Unlike typical convection cells, which rise and fall in predictable patterns, these tunnels appeared to twist and spiral like cosmic whirlpools, moving both vertically and laterally in ways that contradicted traditional magneto-hydrodynamic simulations. Within these tunnels, localized magnetic fields intensified dramatically, creating zones where the energy density spiked to levels previously thought impossible for such confined spaces. These were not transient anomalies. Some tunnels persisted for days, slowly reshaping the surrounding plasma flows as if the sun's interior were a living, evolving ecosystem. Adding to the intrigue, instruments detected bursts of high-energy radiation emerging from these tunnels at irregular intervals. The radiation didn't follow the usual path outward through the corona. Instead, it twisted along the tunnel spirals, creating miniature loops of electromagnetic energy that seemed to bypass the surface entirely before erupting into space. Scientists quickly realized these tunnels could be the missing link to understanding some of the most mysterious solar phenomena. Sudden, powerful flares that appear without clear triggers. Instead of being generated solely by surface sunspot activity, these flares may originate from deep within the sun, where hidden channels of energy accumulate tension until it is violently released. The discovery sparked a flurry of theoretical work, with researchers racing to update models to account for these subterranean plasma highways. Meanwhile, the sun's surface continued to exhibit features that seemed almost eerily conscious. Sunspots, already known as magnetic powerhouses, behaved in unexpected ways during these observations. In several instances, clusters of sunspots appeared to reorganize themselves before the eruption of a flare, almost as though the sun's magnetic field were deliberately concentrating energy in precise locations. Surrounding granules, the convection cells visible on the photosphere, seemed to shift and tilt in response, forming temporary channels that guided plasma toward the sunspot regions. These coordinated motions hinted at a level of complexity far beyond simple magnetic interactions, suggesting the sun might operate with emergent behavior, where the combined effect of countless particles and fields produces large-scale, coordinated outcomes. Adding another layer of complexity were the observations of coronal loops, immense arcs of plasma connecting sunspots across hundreds of thousands of kilometers. High-speed imaging revealed that these loops weren't static structures. Instead, they oscillated, bent, and even collided, generating shock waves that propagated along the magnetic field lines. Occasionally, loops would intertwine, forming twisted braids of plasma that stored tremendous magnetic energy. When these braids snapped, The release of energy sent coronal mass ejections hurtling into space at unimaginable speeds. For the first time, scientists could directly link these braids to subsurface plasma tunnels, confirming that the sun's interior dynamics had a direct and immediate effect on solar weather. Perhaps the most startling discovery came when researchers began to map temperature anomalies in the sun's deeper layers. Using advanced spectrometry, they identified zones that were unexpectedly cool, sandwiched between regions of extreme heat. These cool pockets didn't behave like the surrounding plasma. Instead of rising toward the surface, they sank and twisted, forming vortex-like structures that could persist for hours. In some cases, these vortexes appeared to interact with nearby magnetic fields, creating localized mini-explosions that released bursts of energy into the overlying corona. These challenged the conventional view that the sun's interior heat transfer was a relatively uniform convective process. Instead, the interior was a chaotic landscape of rising, falling, twisting, and colliding plasma currents, an environment that was anything but predictable. Even more perplexing were the observations of intermittent magnetic whirls in the sun's mid-layers. These whirls rotated independently of the larger magnetic field, and sometimes appeared to defy the expected direction of solar rotation. Occasionally, they aligned with nearby plasma tunnels, forming temporary corridors of energy that could guide massive eruptions with alarming precision. The mechanisms behind these whirls remain a puzzle, though preliminary models suggest they may arise from complex interactions between neutral particles and ionized plasma, a subtle effect previously underestimated in solar physics. It was becoming increasingly clear that the sun's plasma was not a simple electrically charged gas, but a deeply interwoven dynamic system where micro-level interactions could trigger macro-level consequences. The solar orbiter's close-up observations revealed yet another strange behavior. The sun's corona displayed synchronized flickering patterns across seemingly disconnected regions. These flickers, visible in extreme ultraviolet and X-ray wavelengths, appeared to communicate energy almost instantaneously over vast distances. The coordination was so precise that scientists began referring to it as the solar synapse effect, drawing an analogy to neural networks in brains. The flickering suggested that the sun could redistribute energy across large areas with remarkable efficiency, preventing localized overloads that might otherwise result in uncontrolled eruptions. The mechanism behind this rapid coordination remains uncertain, but it may involve highly dynamic interactions between twisted magnetic fields, plasma tunnels, and localized temperature anomalies. Beneath these discoveries, the sun's core remained the ultimate enigma. While no probe can penetrate the radiative and nuclear layers at the center, the patterns observed in the outer layers suggested that the core itself might host oscillatory motions far more complex than previously imagined. Tiny fluctuations in the core could ripple outward through the sun's convection zone, influencing plasma tunnels, magnetic whirls, and surface activity. In essence, the sun appeared to operate as a fully interconnected system, where events deep within the core could manifest in spectacular displays of solar weather hundreds of thousands of kilometers above the surface. The star's behavior was no longer the predictable fusion furnace described in textbooks. It was a dynamic, responsive entity, capable of internal communication and energy regulation on almost a conscious scale. The implications of these findings extend beyond astrophysics. Understanding the sun's inner dynamics is critical for predicting space weather, protecting satellites, and preparing for solar storms that could disrupt Earth's electrical grid. But on a more profound level, the observations challenge humanity's perception of stars as static, predictable objects. The sun is alive with motion, energy, and complexity that defy simple categorization. Its layers are a theater of constant interplay where plasma,
magnetism, and radiation dance in ways that are beautiful, terrifying, and utterly alien.